take you on a tour. They didn't do that, right? But they thought the idea was pretty good. So what they actually did do, this is even more astounding in many ways, they actually carved the temple out of the rock and moved it from where it was up to the top of the. Have you been over there?
That's why I guess they should do
So they had to cut it up in pieces and then move the big blocks of the colonnades of the temple. All right, so if we look at the dams in the United States, look at their locations. We'll look at, let's see. So this is the map that we wanted to get to. So there are in total 80,000 dams across the United States. But if you look at them in terms of their existing and potential, you'll see that there's a few really big ones, just a handful of really big ones, and there's a gazillion very tiny ones. So if we look through, so this is 19th century hydropower, and the size of the dot here tells you how much is being generated. So in the 1800s, there was a small dam. This dam is actually a fairly famous dam. It was built. It was the first example of a dam that was built with significant amount of fly ash from coal combustion rather than cement in the concrete. And it's still there. It's actually an example of how well that works. So prior to 1900 is where the red ones. The green ones are from 1900 to 1929. That was actually that was a big dam building exercise. And then 1930 to 1939, this is where we start putting in some of the older dam and some of the really large facilities. And then the really large Grand Coulee, you can see up there, they get larger. And then in the 50s through up to about 1970 was the kind of the dam building. This is when civil engineers were all building dams, and that was a great time. And you can see since that time they have mostly gotten smaller, and still smaller. And that's as far as the data went. In 2008, the government did a big survey on dams. So we kind of went through this surge of large facilities, and now we're down to small facilities. So the future in the United States is, people say that we could add as much as 60 gigawatts of new hydro capacity by 2025 if we did all of these things. So some of them are pumped storage. So this is an energy storage technology, not really a power generation technology where you find a place. So nominally, Utah would be a great place for this. If you have mountains and water, then in the nighttime when there's excess capacity on the grid, the power is really cheap, and you're looking for places to put it. You use it to pump water up a mountain, fill a reservoir at the top of the mountains. And the next day, when power demand is really high, the water runs back down the mountain, and you generate electrical power. So this is a good example of where you think superficially and only about the technical aspects of things. So how much technical sense does it make to pump water up the mountain and run it back down again to make electricity? So you're always going to lose power in that proposition. Right? So the net effect is a loss of power. When you factor in the economics and demand of power, that actually that can be very profitable and very stabilizing on the grid. So you can see a large part of that is pumped storage. This would be dams that would be used for waves, tidal dams, efficiency improvements, and then powering non-powered dams. So there are a number of dams around the world that mostly small, that are mostly for irrigation or flooding or something like that, that don't have power facilities on it. The one that the Jordanelle Dam that you drive by if you drive up to Heber and then up to Park City, the Jordanelle Reservoir is the reservoir you see there on the right side of the highway. And the dam that's there used to be non-powered. We just installed a rated 5 megawatt. I think it actually generates something like 100 kilowatts on average. A small power generating facility at the bottom of that dam to generate some electrical power from the water that is discharged from that dam. And then there's, you can actually use the kinetic energy of water for generating energy and ocean currents. So all of these, this wave, tidal, We'll talk about that in more detail about how that works, and we'll talk about energy storage as well. But if you look at where the growth opportunities are, so these are the sizes of dams that you could potentially install in the United States on places where there's enough water in a river to generate electricity. And then the non-powered dam potential, so most of those are non-powered dams that are greater than megawatts. And if you superimpose that with, so this is where the dams are, and this is, if you look on the resource assessment, and overlay that with the renewable energy generation from maybe that's from hydro. I forgot what that one was. Oh, there we go. There's the solar one. So this is solar power. You can see that where you have solar power, you don't have the hydro power, and vice versa. So they're kind of complementary to one another in that regard. So how does a dam work? So this is one of the simplest analyses that you can do. So you have a reservoir that blocks the water, a penstock, and sometimes that penstock starts up here and sometimes it's down here. It goes through a turbine, go through a hydro turbine, and expands into a river. So a few things to know about dams. First of all, does it matter whether we put this here or up there? Well, from a pressure standpoint, it doesn't matter. It turns out that it matters a lot. In fact, most dams, most modern dams would have 2 or 3 of them at different locations. Because the thing that limits dam production more than anything else is the environmental impact to fish habitat on the river. And so one of the things that a dam does, think about this for a minute. You build a dam to make electricity. What's that going to do to the temperature of the water downstream from the dam? So think it through for a minute. It's going to increase it or decrease it? So take a minute and describe it. So this is what I want you to think about. So if the dam weren't there before you built the dam, the water would go through the same change in elevation from the headwater to the bottom, but it would be banging into rocks and things like that as it comes down. You built the dam, generate power, release the water. What's got to happen to the water temperature? So talk about it for a minute. So come up, we'll vote on it. So let's make the problem as simple as possible and just say, forget that the water changes the amount of water for the time. Let's just say we have a steady state system. So the reservoir is neither draining nor filling, it's just staying the same. But you built this reservoir, you dammed up a bunch of water, and now you're generating electricity. So same amount of water in the stream without the dam and with the dam. The volume of water would be the same before and after the dam. It's just that now you have a big reservoir. Anybody want to, what's going to happen to the water temperature?
I'm going to say it's going to get colder for 2 reasons. So the first is if you build this reservoir, you now are taking water from really deep down in, so you don't get like thermal radiation heating it up. The second is if you're taking power with your turbines out of the water, it's losing the power.
Yep, so 2 excellent answers, all right? So first of all, it's the fact that you're extracting energy from this water. If the water had been just cascading down, banging into rocks and stuff, and it's moving with the same velocity at the bottom in both cases, and it would have been just dissipated thermal energy in the water without the dam there, right? The water will crash down and maybe have waterfalls and lots of spectacular fishing spots, but at the end of the day, it's just a bunch of friction in the water that destroys the potential energy of the water, and that consumes the potential energy of the water that comes down. So the fact that you are extracting power out of it means that had to come from somewhere, and the amount of power that you produce, that you extract from the water, would translate into a change in the water temperature if it were just cascading down the stream. And the second is actually very significant as well. That's why to split these sometimes is that the only place in water that gets very warm is what's exposed to the sun, and that's usually a relatively small amount of water at the top of the dam. So in most reservoirs, some of you, I'm sure many of you have water skied or something. If you water ski the way I do, where you spend a lot of the time underwater, you might have noticed, I don't know if you've ever swum down, you can actually quite noticeably feel in most reservoirs, if you dive down into the water, you can feel the temperature changing pretty easily. So it's the top 10 feet is the only part that gets warmed by the sun, and it gets pretty cold. It's true of the ocean also, by the way. It's even though the ocean has the sun shining on it a lot more brightly than most reservoirs, the top 50 to 100 feet of the ocean gets warmed by the water. The rest of the ocean is almost freezing, so it's very close to the freezing point. So deep ocean water is very cold. So because of that, so the fish habitat is a major consideration, and so they will split this penstock many times and try to pull a little bit of the water off the top that's warm and blend it in with the cold water down here and try to match the temperature for the river downstream to what it was before the dam was there. The problem with that is that in almost any real dam, the top here varies significantly with the time of the year. So where the top is always different. If you put the penstock here, it'll always be underwater. But if you try to put one near the top, it will be under the water sometimes of the year and not other times of the year. So that's why they end up with 3 or 4 of these things sometimes and trying to blend that.
Have they measured like before they did it? I'm sure they probably built some dams that were just like this, and then realized how much colder. Like, have they measured it? Like,
oh yeah, so they're very, very slow. So from an environmental standpoint, the fish have overtaken dam policy. All right. So everything that has to do with the dam these days is it's all about the fish, and so for fish like trout, which can live locally in a river somewhere, if you can just maintain the habitat, the temperature of the water, not flood the streams out, you can actually maintain pretty good trout and bass and those kind of fish that are migratory. Those fish can live with the dam and the water. There will be one population of fish up here and one down here, and only fish stories to tell about the days when they used to talk to one another. But that works for trout. But for migratory fish, most notably salmon, which are actually, salmon and trout are essentially the same fish, except for salmon that grew a lot bigger and became migratory. The salmon populations, these are devastating. So because the salmon are born upstream, they're hatched upstream, they live upstream for a very short amount of time. For reasons that nobody has adequately been able to explain. They would this part is easy to explain. They go downstream and become saltwater fish for most of their lives. And then when it's time to spawn again, somehow they can remember not just the general area, but the actual, they can remember, they can find their way back to the specific place that they were born in. And that's what they want to do, is go back to location where they were spawned, swim back up the stream in the fresh water and spawn again. You put a dam there, and that becomes impossible, and that has seriously affected salmon populations, especially in the Northwest, where they built a dam from the Columbia River with a lot of salmon. For those reasons, those dams would never be able to be built again. So you've probably heard of a bunch of ideas that people had about how to solve that problem with the fish, and so they call fish ladders, and so they'll have little pools of water that the fish can jump from one to the next, and they'll step their way up this thing so the fish can jump from one pool to the next and get back up into the water here. And they are pretty much, so a lot of engineering has gone into those, and they're pretty much useless. So no fish has enough energy to get all the way from the bottom to the top of the dam, jumping from pool to pool. And so then they made what some people call fish elevators, where instead of making fish jump from pool to pool, they actually mechanically move the pool. The fish fill up one pool, and they mechanically lift it up and drop the fish back out the top. Or sometimes they'll try to make them continuous, so have a brother who works for the Bureau of Reclamation, and they call those fish slurry pipelines. It's like pump the fish upstream, and that has not had a good impact on the fish either. The bottom line is, nobody has figured out a way to build a dam that is friendly to fish being able to migrate past the dam. And the impacts have been so severe on fish populations that there are actually serious considerations about removing some of these dams, especially those that are close to the coast, and trying to restore the fish. So, and it's not just fish. There are populations that are indigenous people, in particular Native American populations, whose traditional livelihoods has been, fish are central to their food and to their culture. And by destroying that food chain, you've pretty much destroyed their cultures.
So once the dam has been built, you know, the first couple generations of fish, I can see how it affects that, but why does it keep affecting fish after that?
Well, so what it does is that those generations, many of them just don't spawn, so the total population of fish drops to very low value, to a very low content. But in addition to not being able to migrate past here, the fish want to, so all of the spawning pools are substantially upstream of where these dams are. And that's by design, so they tend to be in relatively slow-moving, sandy, freshwater, cold freshwater, not the kind of relatively rapid-moving market river systems that are downstream of these, and there just aren't very good spawning opportunities, even if you can kill fish to think. You can trick the fish into thinking this is where you were born. It's just not a good environment for spawning downstream region. So there still are salmon. That hasn't completely destroyed the salmon population, but the salmon runs of the bass, and they're pretty well recorded. You know, they were astounding. They still are pretty astounding. But the salmon runs. There was times when you could almost walk across the river. There were so many salmon in it, and those days are gone pretty much because of the dams. There's a lot of salmon during the salmon run, but they're not the big stuff.
What does that have to do with fish fish? But the temperature of the water, does it have a greater effect on how much energy is extracted as like temperature of steam does?
So the temperature of the water doesn't affect the turbine much. We'll talk about the turbine in just a minute, but it does affect the habitat downstream. So in this case, so fish like bass are kind of, they like warm, slow water. Fish like trout like pretty cold water. But if this used to be kind of a bass environment, and you build a dam in it, then the temperature drops significantly, and the native fish, the traditional fish that used to live there, will mostly be killed, and they'll replace them with. And the problem is that trout don't. So we've got this problem right here. You're in the middle of one of the greatest examples of this problem. So Utah Lake is a fantastic environment for bass, and for bottom-dwelling fish. There's a lot of catfish and things like that in Utah Lake. But Utah Lake is full of invasive, non-native species, and so full at this point that they've actually decided to try to kill all of the fish in Utah Lake and see if they can repopulate it. So there's actually a major operation going on out there where they scoop up all of these fish, and this seriously would be a huge business opportunity for some young chemical engineer. So it's just a gargantuan amount of trashy fish that are coming out of the lake, and right now they're just being landfilled. But it's a really valuable source of protein if you wanted to turn it into feed or fertilizer or something like that. It would be a great operation for something. It's really stinky, sloppy mess. But that's what chemical engineers do. They take stuff like that and turn it into valuable products. So there are people who are hired to just scoop up all the fish they can in the lake, and they actually take them out of the lake and kill them all. They haul them off to mostly landfills right now, and we're talking about thousands of tons of fish come out of the lake. Now, we'll probably go on for 5 or 6 years up there before they get the fish populations down to the point where they try to get native fish to grow back in the lake. So that same kind of thing happens when you adjust the thing down here. So the trout don't come back, but you get a bunch of invasive opportunistic fish that come back, and they're not native to that area, and so some people say, well, you know, it's still an ecosystem with fish that live in it, and so to some people, mostly people who are supporters of the dam, they don't see it as so severe, but environmentalists see that as a problem. So let's talk about the types of hydropower. So the most common one that most people think about is impoundment, where you build a dam and dam the water, that is, impound the water. Oh, I've been talking about the turbine. So unlike a gas turbine, when we talked about gas turbines, what did we decide? What is it, the volumetric or the mass flow rate through a gas turbine that determines how much power it's going to produce? The volumetric flow rate, right? So if you were to put helium and argon at the same volumetric flow rates through a turbine, under the same conditions, they would produce the same amount of energy, even though the argon weighs 10 times as much as helium. So hydropower is just the other way around. So it's the mass flow rate, or in particular the change in pressure, the potential energy that generates the power, not the volumetric flow rate. So that's an important difference to think about. Hydro turbines versus gas turbines are quite different in that regard. So impoundment, just back up the water and generate the water from the potential energy. That's by far the most common dam, most common type of electric power plant. Usually there is, in almost all cases, the entire river is impounded. So by contrast, the diversion kind of a dam is where you just take some of the water, you don't dam it, you just find, for example, a waterfall. This happens, by the way, at Niagara Falls. So the water, they didn't dam Niagara Falls, but they generate a lot of electrical power from Niagara Falls, and they do it by building a waterway from the top to the bottom here and divert some of the water that would have gone over the waterfall through the hydro facility and generate the electricity that way. And it's actually, you hear these jokes all the time that people go to Niagara Falls and they say they just found them for tourists. But in reality, at nighttime, the water that flows through Niagara Falls is substantially less than it is during the day. So during the day, they would let the waterfall because it's a famous place and people want to see the waterfall falling in Niagara. But if it's at some time when people aren't able to see the water, they divert a significant amount of it and generate electricity from it. So it's actually kind of true that they kind of turn it on and off for the tourists. So this is sometimes called a run-of-river kind of facility, and doesn't involve a major dam. Sometimes it involves a small diversion dam at the top to capture some of the water, but it doesn't dam the whole river like an impoundment facility does. And then there's the microturbines. This is the one like the Jordanelle Reservoir, where you have relatively small amount of water and a relatively small pressure drop, one or both of those, and they just build a very small facility and generate a little bit of power from a relatively small pressure drop and a relatively small volumetric flow rate. But still, that power turns out to be fairly valuable. It's relatively inexpensive to install, and it's renewable power. So DOE defines a large hydro facilities as having more than 30 megawatts of facility. Small hydropower facilities are less than that, about 100 kilowatts to 30 megawatts. And micro power is less than 100 kilowatts. And a lot of them actually generate, there's a lot of them at that stage. So the analysis here is, this is stuff that you probably learned in high school. So the potential energy is just the mgh, the mass times the height times force of gravity, or rho gh in terms of energy per unit volume. Power is the mass flow rate times gh, or the volumetric flow rate times gh. And that's the total amount of power that you could generate, and if you put an efficiency in front of it, and that tells you how much power you actually do generate. And that's pretty simple to that potential energy analysis is pretty simple. So the turbine itself, it's called a prime mover. So several things to understand about turbines. One, So first of all, this is how a hydroturbine works. It's not like a gas flow turbine. They're almost always radial flow devices where the water comes in through what they usually call a wicket. It comes through a penstock that comes around the outside, and then you have these wicket gates, and wicket gates determine how much tangential velocity the water has as it starts down through the turbine blades. So then the water goes down through the turbine blades, spins the turbine, and comes out the bottom, and we'll look in a minute about there's some good design principles about what you do here at the bottom as well. But attached usually directly to that shaft, on the other end of the shaft is a generator. And so this is we'll start here, but this is also a major issue for wind. So this is going to be generating electricity, but as you change the amount of power, the rate of rotation of this shaft doesn't change. So I'm going to say this, and then I'll tell you that this isn't quite true. But to first order, that shaft rotation rate is always the same, no matter how much power you generate. So you would think maybe that as you generate more power, you're turning it faster and slower. Why can't you do that? Right, so this generator is usually directly coupled to the grid, which means that the rate of rotation of this device has to be synchronized with the grid. And if you let that vary, and if you're generating AC power, you would end up generating a short, and you would blow the whole thing up from an electrical short if you got out of sync with the electrical grid. So for hydropower, so a little bit now with hydropower, but it's fairly commonly now these days with wind power. So the same is true of wind power. When you drive by a wind farm, I don't know if you've ever noticed, all of the windmills are perfectly, they're all rotating at exactly the same rate. At least I look at that and think, how can that be possible? I'm sure the wind is varying, different amounts of wind, different locations, why are they all rotating at the same rate? That's because they have to be regulated to generate at that rate. So how do you change the amount of power that this generates? So one is you can change the flow rate, and the second is through these wicket gates. So these wicket gates can vary the tangential versus the direct energy, and so they can take a combination of the flow rate and how much tangential energy you put into the water. Allows you to vary the amount of force that you put on these turbine blades, even without varying the rate at which the turbine blades are spinning. So the turbine blade is always spinning at the same rate, but if you have, so the least amount of force which you can generate on them is if the water is cutting straight through with no tangential velocity, that pushes them at a certain rate. And then the more tangential velocity that you give them, so then they're going to push on the turbine. So the more the water is swirling in this direction as it goes through, the more force you can put on those blades. The more force you put on the blades, more resistance you can put up here, which generates more power. So you see how that works? So it's not so obvious with hydropower systems that they develop. And it's not actually true that so if you had a bank of several of these, like they have in the Three Gorges Dam, they have two different kinds of turbines that they generate. And all of one kind of turbine would be spinning at the same rate, but it may or may not be at the same rate as the other one, because the actual rotation rate depends upon the winding that you put up here. So in one rotation, how many times does the power go up and down in terms of the AC power that it generates? So it's not true that every turbine spins at the same rotation rate, but it is true that the rotation rate doesn't change, and that any turbine with the same windings would have the same rotation rate. I see a hand.
So if it's hitting the turbine blades with more force, does that mean that like on the top, the generator part, they change something up there? They increase the resistance maybe?
Yeah, so how do you generate electricity? So the thing is, so at the top, you create an electric, so there's, in fact, we will do probably for one of our homework assignments, we'll make a little electric motor. But at the top, you have an electromagnet and a fixed magnet. So the simple way to describe a generator is that you have a fixed magnet that's rotating and an electromagnet that's stationary around there. The more power you put into that electromagnet, the more difficult it is for you to rotate the device. So as it's forced around there, it creates a electrical potential as the magnets cross through. As they go through their similar polarities, And the stronger the magnet is, the more power it's going to produce as one magnet passes through the other. So essentially you generate the more power by creating more resistance by changing the magnetic force of the electromagnet in the generator. And just like, so any of you ride bicycles that have little electric generators on them? Or kind of think of an experience that you would have had where you actually could feel the change in force as you change the amount of power you generate. Sometimes they have, I don't know if any of you work on like running on a treadmill or a stair stepper or something that has an electrical motor attached to it, and you can vary the resistance there. So that's what that's doing, is as you dial in more resistance, it means you have to push harder with a stair stepper. And actually, most of them just have a brake, and you're just wasting energy. But if you wanted to do it elegantly, you could create the resistance of an electromagnetic, and you could actually generate power. I've often thought people that make these, you make a little thing you can pedal, put on your desk and pedal and generate electricity. I've often thought we ought to. So this would be a great cure for teenagers, is that they can play video games as long as they generate all of their power that they need for the video game by their little pedal machine. So that would create some very fit teenagers.
They'd have to pedal pretty hard.
Yeah, you would be exhausted after 5 minutes of video game. Both outcomes are good, right? You're exhausted, but you're not playing video games. So most people could not sustain even. So for a modern laptop, most people could sustain with reasonable effort the amount of power to run a laptop. But, so when you exercise, if you ever calculate actually how much energy you're expending and compare that to even the smallest electrical motor, it gets pretty discouraging. So our capacity for doing work is pretty pitiful in terms of the things that are around us all the time. So there's several different kinds of turbines. These are some of the kinds of turbine systems. The really large turbines are typically Francis turbines. I'll show you a diagram in a minute, but these are built for really high pressure drops, indoor, very large flows. They have the fixed propeller one is an intermediate version. This turbo motor the turbo motor and the belted wheel are examples of what we call impact turbines, and I'll show you how those work in just a minute. The Kaplan one is made for very slow moving water. This is what they would put. This is the kind of turbine they put in to try to capture waves or tidal pools and capture water from that. And then this cross flow turbine is a little bit like what they used to use for steamboats, for example, in rivers and stuff like that. So this is actual pictures of several of those kinds of turbines instead of diagrams on turbine blades. So we talked about the Francis turbine. So the water comes in through this cowling and this casing, and then you have the wicket gates. And the wicket gates are adjusted like this, so they adjust the angular momentum, tangential momentum of the water that comes through here, and then that goes down through the runner blades that you see in the turbine here. It's convert the momentum to power. The axial flow turbines, those just go mostly straight through, and they still have guide vanes, they're called here, or wicket gates. The impulse turbines are different. So this is the way these work. So you have water that comes through, and you actually squirt the water into these little cups. And the cups are shaped like this, so that the water comes in like this, and it leaves relative to the cup. It leaves with the same velocity that it enters in, ideally. So the water will come in and leave like this. But relative to fixed coordinates, ideally this water would be motionless when it comes up. So it would come in with a big jet here, but this blade is moving, and so when it comes off the blade, the water would actually be dripping straight down. If you build it just right, that's the most amount of momentum you can get out of the water. But the fact that you're impacting this on, in this case, a Pelton wheel, you can do the same thing with on the side with the turbo impulse system. So here you just squirt the water onto the side, and these vanes catch the water, and you turn the vanes that way. So how do you tell which kind of turbine you want to you want to use. So depending upon the head or the amount of pressure that you have, and depending upon the flow rate, this is a diagram that kind of shows where you would use most turbines. So most facilities are in this, most large facilities are in this region here where you use Francis turbines. But if you have very little pressure drop, but a lot of flow rate, so this is like, we'll talk about this later, but people capture tides when they come in, and then they try to use as the tide goes out, they try to use the energy from the tide to generate electrical power. So the delta, the change in pressure is very small. There's a large flow rate, the whole ocean coming in and going out. So that's a good use for Kaplan turbines or propellers. If you have a really tiny flow rate but a really high pressure, then you use a Pelton or an impact turbine is usually the best choice. So that's a quick summary of hydropower. Any questions about any of that? So some of the things to recognize, hydropower has had a pretty stable contribution to the total power that we generate over many decades now. Although there's a significant potential for additional hydropower in the U.S., the actual change in hydropower has been near zero over a long time. It's almost none of the facilities have been taken out. A few small facilities have been added that tend to be the microturbine kind of installations that have some local impact, but very little impact on the national or global scale. The largest hydro facilities in the world are not in the United States, unlike most of the rest of the things we talked about. The United States is the biggest and the baddest of the world. They're in places that have large hydro capacities, like China, and coupled with large needs. And as with a lot of other energy systems, China has designed and is designing some of the largest facilities in the world. It has developed the largest facility, probably the largest one that will ever be built. I don't know if anybody will ever build anything again besides three turbines. But they're still building. They're building some others that are comparably sized, just a little smaller. They're under construction. 2 or 3 in China now that are under construction. All right, let's take a short break, and when we come back, we'll talk about wind and then about the example of it. That, by the way, is the most common system that people use to describe reservoirs, is cylindrical fortress. So that should, I don't think there's anything new about that other than using the cylindrical coordinate system to do it. So the adiabatic flame temperatures, you should have been shocked at how high they were. So it's a pretty simple problem. You just set it up and you equate the enthalpy of the reactants and the enthalpy of the products. The constant heat capacity, you can solve that expression analytically. Just put the temperature, adiabatic flame temperature equals a bunch of numbers that you can plug in. So the reason it's so high is that when you burn something in air, so it's, first of all, flame temperatures are pretty high in air, right? So that is 2,000 degrees, that's pretty hot, 2,200 degrees. But 3/4 of air, or not so, 80%, essentially 79% of air is nitrogen, so it just dilutes all of that temperature. So if you take the nitrogen out, you would expect that the temperature is going to increase by a factor of roughly 4, which is about what you got, right? So that's and so now it turns out, anybody know what the surface temperature of the sun is? It's about 5,500 degrees, right? Which is below the temperatures that you calculated for the So in reality, the flames aren't that hot. When you burn something in oxygen, they don't get that hot. But what we assumed in this problem is that the only products were carbon dioxide and water. But at those temperatures, carbon dioxide and water dissociate to form significant amounts of carbon monoxide, oxygen, and hydrogen. So it may sound a little counterintuitive, but at such high temperatures, you can have hydrogen and oxygen in the mixture, in equilibrium. They don't react with each other, even though they're blazingly hot. And that's just the way thermodynamics works. You would think at very high temperatures, if you put hydrogen and oxygen together, they would react rapidly and form water. And there's still a lot of water there, but there's a significant amount of hydrogen and oxygen at that temperature. So they don't actually achieve those temperatures, but they do get up into these 3,000, almost 4,000 degree range. So that's why an acetylene torch works so well, is that it gets so hot that it cuts through virtually anything.
Why don't we use pure oxygen in like coal plants where we're not actually contacting it?
So same reason, and that is that we just can't handle, well, first of all, it's extraordinarily expensive to produce thawing. Air is free and oxygen is very expensive. So you're in the middle of a separations class. I don't know if you have a project, but does he have a project planned in this class where you can do something like that? So, anyway, if sometime at night you're just dying to do some engineering and you're wondering what's an interesting engineering problem to do, and you've already done all the ones for energy engineering, here's a so doing oxygen and nitrogen separation is a pretty fascinating separation problem. Turns out you get it cold enough that you'd make them both liquid, but they both turn liquid. You can't get one of them to form a liquid and not the other one, so then you have to distill them. You put them in a distillation column. And we forget most of the time that 1% of the air that we breathe, which is a lot, 1% is argon. So we just lump that into the nitrogen usually because it's inert like nitrogen is. So then if you want to separate the argon out, then you actually have to do 3 distillations, 1 for the argon and 2 at 1 at high pressure and 1 at intermediate lower pressure to get the oxygen to separate from the nitrogen. And that's all done at negative 200 degrees-ish. They fold into the condenser. That's really expensive. So, but the other reason is that high temperature, we already have way higher temperature than we can use. So that is, when we burn most things, the maximum temperature that we use when we make steam only is up to 600 degrees. If we have a gas that's at 1,000 degrees. So if we could come up with materials that could stand at high temperature, we could, without ever going to oxygen, we got all the way from 600 to 2,000 degrees, then we could move, and that would be a big improvement in efficiency before you even start thinking about oxygen. So the materials one of the problems. Okay, so the last one was the nuclear problem, and you should have found that we generate just about a little less than 1/1000th of the amount of energy that you might think if you just say we're just converting mass to energy in an annihilation kind of a reaction. There's a little over 1,000 times more energy in that reaction than there is in the real reaction, which really just amounts to rearranging the nuclear materials so that they make more stable, which is what's really happening. And the stoichiometries that I gave you there are, in real nuclear fission reactions, you generate a lot of products, but that's actually quite a realistic representation of the overall nuclear reaction of what happens. So the amount of energy that you're generating and the kind of products that you're generating in that problem are both typical of reactors. Cesium and strontium in particular are some of the most common materials that generate nuclear processes. So, any questions or comments about any of that? All right. Did you feel did it give you the preparation you needed to do well on the exams? I hope there wasn't anything that came out of left field and just couldn't have anticipated. So I might do this sometime, but I took an exam when I was a student at BYU once. I still remember, asked the question, a little asterisk. Don't ever read the asterisk. Little asterisk, I'm going down to the bottom of the page. There was a note that said, the first person who answered this problem successfully was given a Nobel Prize. What? So, I was in a class of 3 students, and I still remember at the end of the semester, I was a reasonably good student, but somehow I got an A out of that class, but the average grade in that class was a C. and it was a pretty brutal class. So, but it was.
Did you get a Nobel Prize?
Somebody already figured out that shit. But that is kind of a joke on side. Let's a research problem, put it on an exam and see if somebody else has a good idea. Well, I will tell you, in fact, there's some chance, tell me if you would be interested in this. So, one year in this class, I coordinated some stuff with colleagues in Europe and in China, and we had what we called the Global Innovent. And that was, we divided everybody up into teams, so each one of you would have a couple of teammates here, and 5 in China and 5 in Europe. And using Skype, we gave the whole class a problem. Using Skype, you worked on it here during the daylight hours here, and then we'd pass it off here to China. China would work on it during their daylight hours, and they would pass it off to Europe. Europe would work on it in their daylight hours, and then by that time it's back to our daylight hours, and for a week, this problem just went around the globe. The sun never set for this problem. And the problem we gave them, we told them, so we were told, we're not going to tell you what the problem is until we start with this thing. So the problem we gave them, we said, this is an impossible problem. But we want to see how much progress. So nobody's been able to answer to figure this out yet, but see how much progress you can make in this as a climate change related issue. So I thought that was pretty fun. Would that be? I can probably still get those things set up if I have to do it right now. Make it work. But, are you interested in doing something like that?
As long as the sun's up, we'll be working on that project.
Well, just that while you're working on it, it will be during the daylight hours. Not necessarily have to work on it all of the daylight. The neatest thing of that was just to learn to communicate better. So you've got to be able to work on something and then communicate the progress that you've made well enough that someone else in another country, in another culture can pick it up and make progress on it from that point and not just have to redo what you did. And they're going to do the same thing, and then you get it from somebody else. And learning to figure out what they've done and make use of that and then move forward from there. The natural tendency of everybody is to say, I can't understand this, let's just go back and start over again. Then you don't make any progress. So that's actually a fairly good model in the way a lot of major corporations work with people all over the world. And it really is it's a global community, but it's actually fairly uncommon these days that people move to China or something and work there. But it's very common that you work with colleagues that are all hours of the day you're trying to get things back and forth. All right, wind power. Okay, we're not going to get very far through this, but as you saw from the other diagrams, so wind is becoming more and more a significant contributor, especially to the renewable fraction of wind. In fact, there are several states now that have 10% of their electricity being generated by wind. And I think I mentioned to you the other day, the sum of all renewables actually exceeded the amount of coal power that we generated nationally twice this year, so in 2 months of this year, earlier this year, when coal was very low and renewables were very low. But one of the most important things for us to talk about with wind and solar, wind is the first thing we're going to see, is that this is an intermittent source. And so probably the most common mistake that society makes when they try to compare wind with fossil or nuclear or anything else is that you can't ask the wind to blow when you need the power. So we are very much used to having the power available when we need the power. You just plug something in and you expect with over 99% confidence that the power is going to be there, it's going to be stable. We just don't even think about power going off. It does go off as some kind of a major thing that maybe happens once a year for a few minutes. If it's more than a minute, it probably only happens once every 5 or 6 years for most people, usually during a storm. So if we were to rely entirely on locally produced wind, we would only have electrical power when the wind was blowing. And statistically, the wind blows more commonly at night than it does during the day. And so you can see the problems that creates for the kind of society we have. The cost of losing electrical power is enormous. So, it's enormous in terms of safety. That is, if you lose electrical power, accidents happen all over because traffic becomes snarled. Nobody knows how to behave on the roads. The cost is very high economically from lost production. So most facilities, if they lose electrical power, including, this is a pretty serious safety thing, it gets overlooked. If a building loses electrical power, it is usually not safe to stay in the building because the building's lost its ventilation capability. And if there's something else that's happening that's associated with that loss of electrical power, it's quite possible that there are noxious or toxic gases being produced that aren't going to be ventilated from the building. So the policy at BYU is if we lose the electrical power, we leave the buildings until the power comes back on. And that's probably going to be the policy in almost any place that you work. Hospitals obviously can't, you just can't lose electrical power at hospitals. And data farms are the same way. You just can't tolerate the loss of electrical power from major data centers. So for that reason, people have very sophisticated and very costly backup systems and power supply systems that keep power available when you lose power. So if you were to use wind or solar, in general, you have to do something about this intermittent source of electricity. You generate a lot of electricity during some times of the day and none during most of the day. Even in the best places where wind blows the most, you usually only get about a 30 or 40% capacity factor. 20% is probably more typical for, even as most of you have probably seen the wind turbines that are in Spanish Fork Canyon, and you probably noticed that less than 1/5 of the time they're moving. And so that's one of the problems with wind. So intermittency in general is a problem. So it has a profound impact on the amount and value of produced energy. And energy storage can shift this a little bit, but it won't change it. So there are some subtle things that happen with this as well. So we are still famously incapable of predicting weather with very much accuracy. I still remember when I was a scout. I must have been a scout anyway. We used to go backpacking without any adults fairly commonly. We had this great backpacking trip planned and we listened to the weather station. The weather forecaster's name was Bob Wolf. Quite well known. I lived in Nevada, but he was here in Utah. Nevada doesn't have a big TV station, so he said there's 20% chance of rain on this weekend. Well, that chance never gets below 20%, right? So that's it's always 20%. It's always between 20 and 80. It never gets to 100 and never gets below 20. It seems like so. We left on our backpacking trip and we got soaked, and it was a miserable trip. When I came back, I was wringing water out of my socks, and I wished I had done this. Everybody got the kick out of it. For a moment, I thought, I'm going to send this wet, stinky sock to Bob Wilton just so he understands what 20% chance of precipitation means in practice on the ground. But it turns out that even though we can't predict weather very accurately over 5 or 7 days, we can predict wind if you want to, if you put the effort into it. You can predict the wind quite accurately for about 24 hours ahead of time. So 2 days from now, we can't very accurately tell whether the wind's going to blow or not. Well, even then you can tell. So if there's no cold front moving through, if there's no change in pressure, and there's none on the horizon, then you can be pretty sure that 2 days from now the wind isn't going to be blowing just like it's not blowing today. That is easy to predict. So when the skies are completely clear, and they're clear all the way from here to the Pacific coast, it's pretty easy to say we're not going to have much wind or rain for the next few days. But what predicting the weather means is to be able to say there's a storm coming, and can we predict when it arrives and how big it's going to be and how much the wind is blowing. And that you can do pretty accurately if you don't try to do it much more than about 24 hours ahead of time. So 2 days ahead of time is too much. 24 hours is pretty
It seems to me like you could pair this kind of an energy source with like the energy storage of hydro that you're talking about. So why don't we do more of that with just,
So we'll talk about exactly that. So one of the huge causes, so in Utah isn't one of these places, but most of the rest of the world, some of the United States, most of the rest of the world has what they call it, they have a free market energy system where, so in Utah, if you live in Provo, you have to buy your power from Provo Electric. If you live anywhere else in Utah Valley, you have to buy your power from Rocky Mountain Power. That's the only choice you have. They have a monopoly, and because they have a monopoly, they have a public utility commission that regulates very closely what they do, how much money they can make, and that's the way that the world used to be. But these days, so it turns out like that's a heavy regulated kind of government installation, and like most of those, they tend to be fairly inefficient. So you can generate power much cheaper if you let people choose where they buy their power from, and if you make power generators bid on generating electricity. So the way a big fraction of this world works is that if you're an electrical power producer, you bid typically 24 hours ahead of time, sometimes a little bit more than that, and in 15-minute increments. And so you say, we will produce this much power at this price during this 15-minute window, and everybody sends these bids in, and they're for 15-minute increments. And then the grid operator says, this is how much power I need, so he just rank orders those bids, draws a line at the most expensive one that gets the most amount of power that they think they're going to need, and then everybody gets that price. So even if you bid less, you actually get the price of the last person that comes on the grid. But if you're below that line, you don't get paid anything. And so this makes power producers really pay attention both to price and to their availability. So when you factor something like wind in here, so wind systems are large. They're large. They're larger than most countries in Europe. And so Europe, for example, is one place that has this called a liberalized energy system. And so it's not only possible, but it's common that storms that are bigger than the United Kingdom or bigger than Denmark or as big as Germany come through the system all the time. And everybody can look at that and say, I can tell that 24 hours from now, the wind is going to be blowing. And when the wind blows, there are so many wind turbines that are installed there that the wind energy is going to provide all of the electrical power that people need. And this has happened several times where, for example, the cost of electricity that people charge ends up going negative. That is, the wind turbines have to get rid of this electricity, and they know they're going to be generating a lot of it. So they bid very, very low prices, sometimes negative prices, because it's really expensive to shut systems down. And so some people will build negative prices, and so the whole country will have a power price that's negative. And France and the United Kingdom, who have forever gotten along spectacularly, right? And so this has happened several times, that one of them will see that this is going to happen in the other one, and they will suck all the power out of that other nation at a negative price, right? So they're paying you to take the electrical power out of this. Or think about the people that are running the nuclear plants or the large fossil plants. They can't just turn their plants off, but they're going to lose a lot of money for generating power during this power generation time. And so it's those large plants that provide the reliability of the grid. That is, when the wind isn't blowing, you're completely dependent upon large nuclear or fossil plants that are generating electricity. But when the wind is blowing, they get severely penalized for the electrical power they produce. You add to that the fact that the government, in order to encourage renewable energy, frequently will guarantee a price for wind. So call that a tariff, tariff that they will guarantee. So even though the nuclear plant or the fossil plant will get nothing or sometimes negative values, the wind, the market value for the power is really low, but the wind and the solar facilities get very high rates because the government's created this guarantee, so people will build them and give them some assurance that they'll actually be able to make money. So this intermittency causes really large problems. And it's actually a very real, how many of you live in Provo? Probably almost everybody lives in Provo citizens. So you may or may not be paying attention to local politics right now. But Provo City Council just passed an ordinance that said that if you have solar panels on your roof, there's a fee, a monthly fee that you have to pay just for having the solar panels. It doesn't matter how much you generate. So is that fair? So the rationale for that is that if you generate the solar panels, so Utah has what we call net metering. If you generate solar power from your roof, you can use that to power your home, and you can even put it back onto the grid, and you get the retail cost of power. That is what they would have charged you for power. It will give you credit for anything you put back onto the grid. It'll give you credit at the same price that they would have charged you for the power that you put back onto the grid. But that means that so the cost of power generation is usually less than a fourth of what it costs. The cost of what it takes to generate the power is usually less than a fourth of the honest price for power that they charge you, because you have to build and maintain the grids, you have to collect the money from people, you got a whole bunch of customers, and they have a whole team of people that are trying to send out bills and collect bills and all the hassles that are associated with that. And so the retail cost of power has the cost of power generation in it, but it has all these other things with it as well. And if you're operating the solar panels, the utility will argue you're not helping to support all of that infrastructure, which you need in order to be able to sell your power back onto the grid, and which you need when you're not generating electrical power, if you want to use electrical power, you're counting on that being there, but you're not contributing to it. So that's the justification for the fee. The solar panel people will tell you, yeah, but we paid for this infrastructure to generate this electrical power. Everybody benefits by generating less pollution, less CO2. Everybody else isn't helping us to pay for our solar panels. We pay for our solar panels ourselves. And so that's a debate that's going on right now. So Provo City Council just passed a regulation that said you're going to have to pay for that. The mayor of Provo just said when it gets to my desk, I will veto it. And the city council just said, and we will override the veto. So this is real current stuff right now that will affect each one of you. Not a lot. The fee isn't all that staggering, but the philosophy behind it is a big deal. So all of that is driven by intermittency. So most of this we talked about. So in terms of wind, let's first look at the wind potential in the United States. So here, purple is the highest wind potential, and so it's kind of backwards of what you, well, here's the scale you see over here. So these are the average wind speeds. And so most of you are, possibly many of you are from the western United States, but it took me a while to figure out that all the people in the United States live over here. And out here, by comparison, there aren't any people out there. So in particular, this is mostly corn, and this is mostly mountains, and that's where the people are, right? So, and down here, there's a lot of people. So you can see that the wind potential is lousy where most of the people live, but it's fantastic where the corn and the mountains, and Wyoming in particular is one of the best states in the country for wind. And that's another one of the problems, is that we can generate a lot of wind, but the best places to do it are places that are relatively large distances from where most of the people live. But you'll also notice that once you get offshore, the wind potential offshore is fantastic just about wherever you are. Well, down here. So both solar and wind are pretty lousy when you get down here, but along most of the shoreline of the United States, there's a lot of very high quality wind potential. So the reason that people like to build wind installations offshore, so there's an obvious reason not to do it. It's way more expensive to build a facility, and it's what may not be as obvious. It's also way more expensive to maintain a facility. So building it offshore has some downsides, but the upside is that the wind quality is much better offshore than it is onshore. And onshore, there are places that are pretty good. So Texas generates a lot of wind. Wyoming generates actually a huge amount of wind. The state of Wyoming, they export most of the electrical power back here. Right now, trying to permit another grid installation, a power line that will go from here to Delta, connecting to the one in Delta, and sell this power in California because it's CO2 neutral from the city. So the cost, the wholesale cost of power generation in Wyoming is about 2 cents per kilowatt hour. California, it's 13 cents per kilowatt hour. So if you can get that power in California, you can make a lot more money for that. So that's some of the challenges with wind. The wind energy costs have come down dramatically recently. So this shows nationwide energy costs. The average levelized cost for a power purchase agreement. And so they're now down where they're on the order of what coal-fired power plants are. So wind actually competes fairly well with coal in terms of the cost of electrical power, depending on the region you're in. If you're in good places for wind, then the cost for electrical power is not so high. So let's talk a little bit about the technologies and then we'll finish.
Is that independent of government subsidies?
No, it's highly dependent on government subsidies, but the subsidies right now. So if you look at the unsubsidized cost of wind power, it's fairly cheap right now. So it's comparable to other options that we have for power. So it's probably still it's probably a little less than nuclear. It's certainly less than small installations of any type. It's starting to compete with large installations of coal and natural gas. Now, it's probably about the same as coal right now, but coal is above what natural gas combined cycle systems would be. And that's where most of the new installations of large-scale installations of natural gas combined cycle installations now, coal and nuclear and wind and solar, none of them can compete with that, but it's fairly close to that. It's within a factor of 2 of that. So these are the kinds of, these are the places where you get a lot of this information. These are the kinds of wind turbines that are being built. And we'll just go through a little bit of history and a little bit of a talk about how this works. So you've all seen these pictures of, we call this the American farm windmill design. And that turns out for relatively low velocity winds, this is an excellent design. This was used to pump water, not to make electricity most typically, but those were all over the western United States. They're actually fairly hard to find these days, but they're pretty good designs. By comparison, this is a modern wind turbine in the distance there. So a couple of things to recognize. One is so these are installations. This is just outside of Copenhagen in Denmark, and this is a fairly typical modern wind turbine installation. You see here, that's actually fairly small. I'll show you the sizes of them in just a minute. And just history. So you can read through this history. I might not go through too much. Just recognize that wind started being used as 7,000 years ago. So it's an old technology. Wind turbines are fairly new. We'll go through the installations around the world when we get to talking first about the sizes of these systems. So most people have no appreciation for how big a modern wind turbine is. So this is the Vestas 2. So this is one turbine that has a 2 megawatt capacity. The largest ones that people are building right now are 3 times this size. They have actually built some 10 megawatt facilities, 10 megawatt individual towers. But even at 2 megawatts, so this is a Boeing 747 aircraft, and this is the span of the rotors on the wind turbine. And these are gargantuan facilities. They are almost unbelievably large. To put that in another perspective, so this is a 5 megawatt wind turbine standing next to the Statue of Liberty. And so these are really, really large facilities. So think mechanically about what it takes to, you've got a lot of stress on this very long arm that's all being supported by that rotor. And that rotor is 600 feet in the air on the top of a tall tower. So the mechanical designs of these systems are astounding. And actually the most vulnerable part of them isn't even obvious from this. That is, this has to be tied into a gear hub that's in that rotor, and keeping that gear hub from tearing itself apart when you have, the forces on here are not constant. The wind blows and it comes in gusts, and so you have surges of forces inside this gear hub. And that's actually been the most difficult thing in building these turbines, is to figure out how to build these gear facilities and not just have them tear themselves apart under the fluctuating forces that people.
Is that height to the center of the rotor?
Yeah, this, well, I've got both of those heights. This one is probably to the top of the 600 feet, is pretty tall. That's probably to the top of the top tower. So the reason I can remember that is, anybody know how tall the tallest tree is? Excellent. All right. So 360-ish feet, and you must know where they are. Did we talk about that today? Okay. So the coastal redwoods are the largest trees, and they're about this tall. So that would make 600 feet. So they're taller than so these are some of the typical Rs. So this is the type, this is the axis height, the rotor height, and max power that's being produced. So the 6M repower things, so they'll produce, these are the ones that are actually in installation, in commercial installations around the world. And they get up to about 6 megawatts of capacity. So there are designs for, and some demonstration installations, but not large-scale commercial installations of wind turbines that are up to 10 megawatts of electrical power, but they're still trying to solve that gear issue, among others. So the largest windmill is actually the Enercon, the second one on this list. It's up to 7.5 megawatts. And so this is what it looks like. So from a distance, it's not so obvious how big that is, because if you're standing out from looking at it from a distance. But this is a door in the facility that gives you access, and these are actually some cows in the field you see out there. And that's a pretty major installation. So you can build these onshore or offshore. There is technology that Japan's trying to develop right now, where they can be built offshore, but not on fixed platforms, on floating platforms. So if you could come up with a technology that would work like this is they've built a few of these to try to get them to work. There's floating windmills, then you could actually take a whole wind farm and park it in the water. It'd be a lot cheaper to build this way. Just anchor them out in the far ocean. So some of the things that we'll start next time, we'll talk about some of the statistics and look at the parts and how they work, and look at the analysis for how to analyze wind farm. But some of the societal issues that aren't so obvious, people get really excited about wind farms. The people who have the most windmills, so as a percentage of electrical power, that's Denmark, and in total that's Germany, and they're right next to each other. So there are huge wind farms there. Denmark can provide 100% of its electrical power when all the windmills are operating. That's actually a huge problem for them, because it goes, when a storm comes through, it goes from 0% to 100%, and then over a period of maybe 15 minutes, it goes from 100% back to 0%. When the storm goes through, you have to be able to bring something else online in that time frame. But people also find them quite objectionable. So it turns out they look quiet, but they are very noisy. If you've ever stood close to them, they make a lot of noise, and but more just the presence of them in their rotation. I actually think it's kind of relevant, but I kind of like a lot of things that most people don't. So I drink orange juice, and sometimes I drink lemon juice. So just wakes you up, all right? Pure lemon juice. But when you, so the rule in Denmark right now is that you cannot build another wind turbine that you can see while you're standing on land in Denmark. So they either have to be beyond the horizon offshore, or you can replace an existing windmill with a new windmill. You can't build new windmills because people find them unnerving. Some people, they say would be headaches just to see them. So they're fairly controversial, but they are of absolute amount, so in terms of percent, solar is growing faster right now. In terms of the absolute amount, both in the United States and globally, they're the fastest growing source of renewable power. So we'll talk more about the next time. That's it for today. Oh, your homework. So by 10:30, by 11:30, I'm going to give another lecture for another class at 10. So by 11:30, I will make sure that the ones that wasn't, I looked at them this morning and I think